Chapter 17. So, in chapter 13, we looked at cardiovascular, we looked at blood, and we talked about a little bit relative to the purpose of exchanging respiratory gases for oxygen and carbon dioxide. Then in chapter 16, we looked at the respiratory end of it. Now we're going to get to the nitty-gritty of the actual exchange at the capillaries, okay? So, when you're looking through the arterial blood, meaning I'm going from the left heart to the systemic capillaries, or from the right heart to the pulmonary capillaries, the oxygen and the carbon dioxide levels in each one of those individual systems stays relatively the same. Okay, what does that mean? And we talked about this when we were talking about active and reactive hyperemia, thank you. Active hyperemia and reactive hyperemia, okay? And we said that if things are normal, the amount of O2 that is brought into our bodies is going to be the same amount of O2 that is used by our tissues, and the amount of CO2 that is released from our tissues is the amount of CO2 that is released from the alveoli, and that gets us at a homeostatic balance. So we're going to look here. When I look here, if we look up at the top, I see that my oxygen coming in from the atmosphere to the alveoli is to a single alveolus is about 250 into the lungs is about 250 mLs per minute per lung, okay, which is why we have about 500 mLs between the two lungs. Then that's the same rate that it goes from the alveolus here into the pulmonary capillaries. Then it's going to go through the pulmonary veins, left heart, systemic arteries until we get down here. And you would expect that if I have 250 mLs of oxygen coming in, that I would have 250 mLs of oxygen going to the tissues. And that if I had 200 mLs of CO2 going out, I had 200 mLs of CO2 leaving here. Does that make sense? So that's normal homeostatic levels. Really quickly, some anatomy. The function of the respiratory zone is to exchange gases. So the conducting zone is to bring the air in and out. The respiratory zone is where we actually have that exchange between the air in the alveoli and the respiratory gases in the blood. What's the mechanism of action? Diffusion. Okay. If you don't know diffusion by now, I suck. Okay. The structures of the respiratory zone include the respiratory bronchioles, the alveolar ducts, alveolar sacs, and alveoli. This is why it's often called a respiratory tree. Okay. This is my pulmonary artery going to the lungs. This is my trachea going to the lungs. Anyone figure out what I hate about this picture? What does it say these are? What kind of arteries?
Pulmonary.
Pulmonary arteries. What kind of blood do pulmonary arteries carry? Right? Oxygen 4. And yet they make these red, which makes it look as if it's oxygen rich. I don't like that. I didn't do the cast. I have no say. Okay? So here, this is going to be my pulmonary trunk branching to my left and right pulmonary arteries, which will branch to my arterioles, blah, 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 until I get down to all of the individual alveoli, by the way, none of which you can see. They're microscopic. What you do see is running side by side is the, well, actually, it's not the alveoli that you would see here. It's the pulmonary capillaries running side by side with the trachea that goes into the primary bronchi, secondary bronchi, tertiary bronchi, bronchioles, blah, 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 down to the alveoli. And notice with all of these, you see that the respiratory piece, which is this yellowish, and the cardiovascular piece, which is red, all run together because that's ultimately to get to our respiratory alveoli, which are surrounded by our cardiovascular capillaries. Notice, by the way, these are those pores that I was talking about that distribute pressure, because otherwise, when I inhale, if the air first got to these, and there was so much air that it had to be able to spread all the way out to here, if these weren't interconnected to distribute pressure, these would blow out. Okay, so what this does is it results in equal pressure distribution. Okay, so here you can see a bronchiole. I'm not going to ask you this part of the anatomy, okay, but you see a terminal bronchiole branching to respiratory bronchioles. Off of those, we have our alveolar ducts that go to our alveolar sacs, which have numerous alveoli. What does that actually look like? Well, it looks like this. Okay. So each one of these spaces is an alveolus. What this is a cast of is the blood vessels. So here you can see we have all, no, sorry, wrong picture. What this is a picture of is the respiratory. So this is the tissue that makes up the bronchiole. This is the simple squamous epithelium that makes up each alveolus. Now, back, this is a spherical alveolus, right? But if I cut it open, I see these spaces. Here, what you're seeing are these spaces where the air is. Okay? So this is the tissue of the alveolus, and this is the space where oxygen is actually exchanged. Exchanged with what? Well, it's exchanged with the pulmonary capillaries. Okay? So surrounding each alveolus, I have my pulmonary capillaries, because between the alveolus and the capillaries, we have capillaries, site of exchange. In this case, what are we exchanging? Respiratory gases, oxygen and carbon dioxide. So let's take one of these and let's blow it up. Okay. When I look at this blown up, this inside represents a single alveolus. Notice that it is, and you can see them here, it is simple squamous epithelium. Simple, only one cell layer thick. Squamous, flat, wide. Right? Maximize diffusion. Right? You want that area as small as possible. Type 1 alveolar cells are the ones that make up that simple squamous epithelium. Those are the epithelial cells. These type 2 alveolar cells, those are the ones that release surfactant. Those are the ones that prevent or stop the alveoli from collapsing. Here, these purple are the alveolar macrophage. They clean up whatever debris makes it all the way down to the alveoli. And then these are the alveolar pores that distribute that the gas and therefore the pressure. So each one of these that you see, those are the epithelial cells that make up the alveolus. Here, surrounding it, you see there are numerous capillaries. What do we know about the cell construction of capillaries? They are one cell, so they are simple, and they're also squamous, they're flat. So these are also simple squamous epithelium. They are attached to one another through what kind of membrane? What do we call that? A basement membrane. So when we look here, because what I've done is I've taken and I've blown up a little section right here. So when we look at that, we see that our respiratory gases need to move back and forth between our alveolar airspace and our capillaries. In order to do that, there are 3 barriers that they have to pass through. Barrier 1, not in that order because it depends on which way we're going, right? One of the barriers are the type 1 alveolar cells, simple squamous epithelium. Also, the capillary cells, simple squamous epithelium, and the connective tissue that attaches these two together, which is the basement membrane. In other words, the thinnest possible membrane between 2 adjacent tissues. And we're going to see this again when we get to the urinary system. Okay? So when we look here and we're looking at exchange, gases move from the alveolar space into the pulmonary capillaries and out of the pulmonary capillaries into the alveolar space down their pressure gradient. Okay. All right. I love this picture. This is actually showing the pulmonary capillaries. Here's a single alveolus, and you can see how the red blood cells line up single file to go through these very, very small capillaries in order to maximize the exchange, not of the blood vessels, but to maximize the exchange of respiratory gases between the alveoli and the plasma that includes the red blood cells, which is what carries most of the oxygen and a little bit of carbon dioxide. So again, this here, my simple squamous epithelium from my alveoli, my simple squamous epithelium from my capillary, and my basement membrane in between them, that is called the respiratory membrane. Tiny, 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 tiny. If you were to take a strand of hair and you were to divide that strand of hair into 1,000,000 pieces, all right, already crazy small, and then you took one of those pieces, one of those 1,000,000 pieces, and divided it by 5, that's how thick this is. What does that mean? It means way too small for my brain to understand. I see Brittany doing the same thing. Okay. The point is super, super, super thin to maximize diffusion. Okay. Let's go back to our ideal gas law. Okay. The pressure of a gas depends on temperature, number of moles, and volume, right? We just looked at this. PV equals nRT. So if I wanted to look at pressure, because that's what we're talking about here, we're talking about the partial pressures of gas, then I divide both sides by V so that I find that the pressure equals the number of moles, gas times temperature over volume, okay? So that's just the ideal gas law. But I know I mentioned to you guys last time we did respiratory that when we talk about the pressure of air, the pressure in that air is made up of what we call partial pressures. And the partial pressures are the pressure of each individual gas that contributes to the entire pressure. So remember we talked about pushing on the door, and we said if I just measure what the force is on the door, that's the total force, that's the total pressure. But if there are 3 of us pushing on that door, the partial pressure would be our own individual contributions to that total pressure. Okay, so when we're talking about gas mixtures, by definition, a gas mixture has 2 or more gases in it. So the total pressure of a gas mixture is the partial pressure of gas 1 plus the partial pressure of gas 2 plus blah, 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 however many gases we have. So the partial pressure of the gas depends on what fractional concentration of the gas is in that total. So what does that mean? That means if I push twice as much as Reagan, my partial pressure is bigger than hers. By how much? Twice, because I applied twice the force. Why did I apply twice the force? Let's pretend there's twice as much of me. Remember, pressure is related to how much? It's related to concentration. So, if I want to know a partial pressure of a gas, given that I know the total pressure of a gas, what I say is, all right, here's my total pressure, which is easy enough to measure. And I know that this gas mixture is made up of X% of gas A. Then I say if I have 20% of this total being gas A, then I take the total pressure, multiply it by 20%, and that tells me what the pressure of gas A is. Does that make sense? Okay, because these are calculations that I like. All right, so when we look at the air that we breathe, under normal circumstances, 78% of our air is nitrogen. That's a lot. Notice it's not just we say nitrogen is the majority. It's not 51%. 78% of the air that we breathe is nitrogen. Okay. that's not really what we're concentrating on when we're looking at our respiratory gases. 21% of the air that we breathe is oxygen. Okay. CO2, remember when we were doing epinephrine, norepinephrine, and dopamine was CO2 is nitrogen, 78, 79%, really should say 50%, okay? Oxygen, 21%, carbon dioxide, 0.03% of 1%, okay? What makes up the rest of it? A whole bunch of stuff. Notice that argon is way more than CO2. Argon is 0.9%. CO2 is 0.03%. So then why don't we talk about argon? And why don't we talk about nitrogen? Because those aren't involved in what the body needs. It needs oxygen, it makes carbon dioxide. So that's why those are the ones that we look at. Okay, so if we want to look at the composition of the air, again, we had our equation before that said the pressure of our gas mixture is equal to the partial pressures of gas 1, gas 2, gas 3, blah, 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 blah. So, using this, the partial pressure of gas A, again, is the total pressure plus the fraction or the percentage of the total that is made up of that given gas. Okay, so just abbreviating it, the partial pressure of gas A is the atmospheric pressure times the percent of gas A. All right, so let's start with atmospheric pressure. When we were comparing atmospheric pressure to the pressures inside the alveoli and inside the intrapleural space, we just said we're making that pressure neutral. We're calling it 0. But now we actually want to look at specific pressures. So I told you earlier, if I were to take a column of air from the ground up to the atmosphere, we define that as 1 atm or 1 atmosphere, which is a unit of pressure. There is a different unit of pressure that we can use. Just like I can use Celsius, I can use Kelvin, I can use Fahrenheit, right? They're all measures of temperature. They're just different ways of measuring that same thing. Okay, so atmosphere is 1 unit of pressure. Okay, another unit of pressure that you may be familiar with, especially when it comes to the tires of your car, is PSI, pounds per square inch. Okay, the pressure that we're going to use here is millimeters of mercury. And that 1 column of air, that if we're describing it as atmospheres, is 1 atmosphere, is the exact same measurement as 760 millimeters of mercury. Okay, just different way of saying the exact same thing. For example, when we talk about the temperature at which water boils, we're talking about Celsius, it's 100 degrees. If we're talking about Fahrenheit, it's 212. We're getting to the same end result, right? But the units of measurement are different. That's all that's different, okay? So 1 atmosphere is the same as 760 millimeters of mercury. All right, so if I want to figure out the partial pressure of gas A, and again, we're talking about air, I know that the total pressure of my atmospheric gas is 760. So to figure out the partial pressure of gas A, I need to know how much of gas A is in the air. So let's say for right now that we're going to call gas A nitrogen. So then my partial pressure of nitrogen is the pressure of the atmospheric gas times the percentage of nitrogen. We said the percentage of nitrogen is about 79%, okay, which is 0.79. So when I want to get the partial pressure of nitrogen, I take my atmospheric pressure times the percent of nitrogen, which is 0.79, and that tells me that the partial pressure of nitrogen in the atmosphere is 600 millimeters of mercury. So of this 760 millimeters of mercury of pressure, 600 of that comes from nitrogen. Why 600? Because nitrogen is 79%. 79% times 760 gets me my 600. Does that make sense? Ready to do it again? Okay, let's do it again this time with gas A being oxygen. Okay, so we're going to do it the same way. The partial pressure of oxygen is 760, my total atmospheric pressure, times the percent of oxygen. What percent of oxygen in the atmosphere? 21%, represented mathematically. What does percent mean? Per 100, right? There are 100 cents in a dollar per cent per 100. So if I take 21 divided by 100, I get my fraction, 21%. Okay. So I want to figure out the partial pressure of O2, my total atmospheric pressure times 21%. And I find that of that 760, 160 is oxygen. Okay. Once more with feeling. What's the other one I'm going to do? Carbon dioxide. So in this case, A is CO2. So partial pressure of CO2 is 760 times the percent of CO2 in atmospheric air. We said the percent of CO2 in atmospheric air is 0.03%. So I divide this by 100, getting 0.0003. So the partial pressure of CO2 is the 760 times 0.0003. Of the 760 millimeters of mercury of total atmospheric air, 1/5 of 1 millimeter of mercury is carbon dioxide. Okay. So let's take this total that we looked at before. Total pressure of a mixture is the added pressures of each individual gas, the added partial pressures. So in air, most of it is nitrogen. We're concerned with oxygen, and we're concerned with CO2. We said on the previous slides that the PN2 partial pressure of nitrogen is 600 millimeters of mercury. We said that the PO2 is 160 millimeters of mercury. And we said that the PCO2 is 0.2 millimeters of mercury, which gives me 760.2 millimeters of mercury. If something costs you $760, do the 20 cents matter? No, right? So that's why when we describe this, we say 760 millimeters of mercury. And notice the vast majority of that is nitrogen. The next largest piece is oxygen, and the partial pressure of carbon dioxide in the atmosphere is super, 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 super low. Why is that important? Because that's what allows that pressure gradient for CO2 to leave. If the pressure of CO2 in the atmosphere is always super, super, super low, then the CO2 inside our alveoli is going to move down its partial pressure gradient. Because remember when we were talking about concentration gradients, and we said that each molecule moves down its own individual concentration gradient? Each gas moves down its own individual partial pressure gradient. Okay? All right. So let's just go ahead and look at this. Okay, so as we just said, gases diffuse down their pressure gradient from high pressure to low pressure. In gas mixtures, gases diffuse down their own individual partial pressure gradients. So from that own gas's high partial pressure to that own gas's low partial pressure, a particular gas diffuses, as I said, down its own partial pressure gradients, and the presence of other gases, when we're looking at that gradient exchange for any one gas, is independent of any of the other gases. So when we're looking at the exchange of oxygen, the only factors that come into play are the partial pressures of oxygen between our two areas of exchange. Doesn't matter what nitrogen is doing, doesn't matter what CO2 is doing, none of that matters. All right, so now let's go back to here. Where am I going to start? We can start anywhere. So let's start up here. And I'm going to start with oxygen. In the atmosphere, the partial pressure of oxygen we calculated is total atmospheric pressure 760. The partial pressure of oxygen we calculated is 160 millimeters of mercury. Okay, so that's the PO2 in the atmosphere. Inside the alveolus, the PO2 is 100 millimeters of mercury. Why is it not exactly the same? Because some of that oxygen is constantly going into the bloodstream. So the amount of oxygen is going to be less, which is what we need in order to ensure that oxygen moves out of the atmosphere into the alveoli. Okay? So then, as a result of the pressure in the alveolus being less than the pressure in the atmosphere, oxygen moves in. Now, let's look at the oxygen content in the pulmonary arteries, because it's the pulmonary arteries that are coming into my pulmonary capillaries. The partial pressure of oxygen in my pulmonary arteries is 40 millimeters of mercury. Where does that number come from? You'll see as we go all the way around. Okay, so for right now, just take it as because I said so until we work the entire circuit. So when my blood comes into the pulmonary capillaries, that oxygen poor blood, the oxygen content in my pulmonary capillaries at the very beginning, before I started my exchange, is 40 millimeters of mercury, right? Let's take and let's blow that up. Okay, so I'm going to take this and I'm going to blow this up. Okay, so PO2 in the air is 100. PO2 in the alveolus is 100. Did I say that wrong? PO2 in the atmosphere is 160. PO2 in the alveolus is 100. Oxygen moves down its own individual partial pressure gradient. It moves out of the atmosphere into the alveolus. Inside my pulmonary artery, my partial pressure of O2 is 40 millimeters of mercury. So oxygen is going to move down its gradient here from 100 down into here where it's 40. So my PO2 here at the beginning is 40, right? Mm-hmm. But then as I move through here, what's oxygen doing? It's moving in, right? Which means what's going to happen to my PO2 in the pulmonary capillaries? It's going to increase. So I go from 40, 55, 70, 85, up to 100. Why do I stop at 100? Because that's what the PO2 is in the alveolus. So now these are at equilibrium. There's no reason for more to come in because these pressures are now the same. Good job, Ashley. Right? So that means that my blood that leaves my pulmonary capillaries through my pulmonary veins is going to have a PO2 of what? 100. Everybody follow that. Okay, so now let's go back to our big picture. So here we're at 100. Here we're at here, 100 until I get to my systemic capillaries, which are the site of exchange, right? So now I'm going to look here. Oh, I'm sorry, I forgot. So 100, 100. Now I'm going to get down here to the cells. And the PO2 in the cells is 40. Why? For the same reason that the PO2 in the alveolus was less than the PO2 in the atmosphere. Because the PO2 in the alveolus is less than the atmosphere because oxygen is leaving the alveolus and going into the pulmonary capillaries. Here, the PO2 in the cells is less because the oxygen that comes through is getting used up in what process? Cellular respiration, right? That's the whole reason we do this. It's because cellular respiration makes ATP, byproduct being CO2, okay? So even though this is coming in with a pressure of 100, oxygen is going to move, but the pressure in the cells maintains 40 because as that oxygen comes in, it's being used. So now let's blow that baby up. Okay, so pressure coming in from my systemic arteries is 100. The PO2 in my cells is 40 because that O2 is continually being used. So O2 moves how? Down its pressure gradient. So it's going to move out of the cells into the tissue. So when I start here, I'm looking at my PO2. What's my PO2 start at? 100, right? And then some of that oxygen is going to leave, and it's going to do what? It's going to decrease to 85, 70, 55, down to 40. Why does it stop at 40? Because now it's at equilibrium with the cells. And so then, when we leave and we go into our systemic veins, our PO2 is 40. Let's go back to our big picture. So here again, when we leave systemic capillaries, PO2 is 40. Oops, what did I do? don't know what I did. Okay, PO2 is 40, and that's why, remember here, when I first put this up and I said this is 40, and I said for now, trust me. Now you see why. And this is how oxygen exchanges again and again and again through the system. Is oxygen our only respiratory gas? We go till 125, right? Yes, okay. Okay, because now we're going to look at CO2. Okay. And I'm going to ask you to do the same thing we did last time. For right now, just start by taking me at my word. In my pulmonary veins, which are oxygen rich, that means they are going to be CO2 poor, right? So when I started my pulmonary veins, my partial pressure of CO2 is 40, okay? Then I go through the left side of my heart, and then I go into my systemic arteries, and my PCO2 is still 40. How come? Because I've had no sites of exchange, no capillaries yet. Then I come down here to my cells. So let's take this and let's blow this up. The PCO2 in my cells is 46. How come? Because CO2 is being produced as O2 is being consumed. That's the byproduct, as Ashley said, of cellular respiration. Okay? So I'm coming in with a PCO2 of 40. The PCO2 in my cells is 46. So how's CO2 going to move? Down its pressure gradient, out of the cells into my systemic capillaries, right? So we're going to do the same thing we did with the oxygen. When my PCO2 enters the systemic capillaries, what is it? It's 40. As I go across, what happens to the amount of CO2 in my capillaries? It increases. And it's going to increase until we reach 46, because that is then equilibrium with the PCO2 in the cells. And when there's equilibrium, there's no net change. So then going into my systemic veins, my PCO2 is 46. So let's jump back out. PCO2 is 46. Systemic veins, right heart, pulmonary arteries, still 46, right? So now let's take this and blow it up. Okay, we know that this is 46 going in the alveolar air, not in the atmospheric air. In the alveolar air, the PCO2 is 40. What did we say the PCO2 was, by the way, in atmospheric air? 0.2 millimeters of mercury. So you can see there is a big push to get CO2 out of the alveolus compared to the atmosphere. Right now we're looking between the alveolus and the pulmonary capillaries. So we come in with 46. This is 40, right? So how's CO2 going to move? Down its concentration gradient, out of the pulmonary capillaries into the alveolus. We come in with a pressure of 46. As I move across, it's going to drop until I end up at 40. So then the PCO2 in my pulmonary veins is 40. As I mentioned before, in the atmosphere, it's 0.3, 0.2. It depends on what reference that you look at. So CO2 is going to go from the alveoli out into the air, which is why here, again, where I said, take me at my word to start, now you see why this is 40. Almost done. Okay, so here we're looking at the whole picture with the CO2. This whole busy picture, which hopefully isn't as busy now when you look at it, is how you have the pressures of both O2 and CO2 between the atmosphere and the alveoli, how you have the pressures of O2 and CO2 between the alveoli and the pulmonary capillaries, how that ends up with our O2 and CO2 levels as we go through pulmonary veins, left heart, systemic arteries, the change that occurs between the systemic capillaries and the tissues, resulting with our values in our systemic veins, right heart, pulmonary arteries, back to where we started again.